Hi guys, today now we're going to look at impact tools, where you can use them, where the advantages are with them, and then some limitations on their use. Now we're going to concentrate on battery powered tools, as air powered impact tooling, it requires another conversation in terms of air compressor specification, air delivery, working pressures, and air consumptions by the tools. So cordless is what we're dealing with. Now, effectively what impact tooling is rotary tooling with a rotary percussion, right? And that differs from a normal hammer drill, which hammers in and out and is used for drilling holes and excavating material out of holes in a wall. All impact tooling operates on the same basis of a percussive force as it's turning fasteners or trying to fasten or unfasten stuff. Now, you will see impact tooling with an IPM or a BPM rating, which is impacts per minute or beats per minute. But this will only tell us so much in terms of its fastening capabilities. To give you an example now, a big hammer is going to carry more force per strike than a small hammer, and the same principles apply to impact tooling. So what we're looking at is the amount of force that we're capable of delivering. And in impact tooling, this force is classed as Newton meters or pounds foot or foot pounds. Now, for reference sake, 1 Newton meter is equal to approximately 3/4 of a pound foot. So here on the table, I have 3 impact tools. I have an impact driver rated at 165 Newton meters. I have an impact wrench with a 1/2 inch head on it, rated at 418 Newton meters. And then I have a very large impact wrench with an inch drive head in it that's rated up to about just over 2000 Newton meters fastening capability. Now, the difference between an impact driver and an impact wrench is primarily its work holding or the bit holding capability at the front. Impact drivers, generally, they have a little slot at the front here, or sort of a ball bearing system, which clamps into 1/4 inch or 6.35 mil hex drives, and the other end of that then accepts a magnetic, or it's a magnetic retention mechanism for screwdriver bits or Torx bits, or whatever tooling you want to put in it. So that generally just slots in there and it fixes itself. Now the impact wrenches themselves come in a range of different sizes. I think you can get 1/4 inch, 3/8, 1/2 inch, 3/4 inch. Inch is generally the biggest. There's 2 different styles of socket connection to this. Okay, and if we look at the impact socket there, we'll be able to see a hole in that. That mates up with this little pin here at the front of it, that detente pin, and it slots on and off just like that. A different style of retention mechanism then is called a hog ring, and in this particular example you can see this little spring clip here, and that spring just holds the socket on there. Now, the advantages of the spring clip is that it's easier to get the sockets on and off, but the advantage to the pin retention mechanism is that they're held much more securely. So depending on your use case, if you're changing sockets all day long, a hog ring style is more suitable, and if you're doing a lot of the same type of fasteners, then the pin retention mechanism is probably the one to go with. Now, in terms of tooling, I just point out that if you are using impact tools, it's very important to use impact sockets or impact bits which are appropriate for use. Generally speaking, these will be sort of fairly well labelled, and here's an example now of PosiDrive 2 bits, and they're classed as impact torsion, so it'll have impact or torsion classed on it somewhere. Now, in terms of sockets then, you'll find 2 different types. I will try and catch this on camera now if I can get the writing. Okay, this is a 24 mil socket, and down the bottom there you can see CR-MO, and that CR-MO stands for chromoly, which is chrome molybdenum, and it's a very strong alloy of steel. In addition to the alloy makeup, you'll also find that impact sockets are generally 6 point, which means that there's just 6 acceptance points there, as opposed to a normal ratchet socket, which in this particular instance is a 12 point. Now the advantage of the 6 points is that you can have a much thicker wall, but the disadvantage is that to actually mount the socket onto a nut, you might have to turn it quite far, up to 60 degrees, to get it to mate with the head of the fastener, as opposed to 30 degrees or half that amount, because you have much more acceptance points on this. Now this here is, we'll see it there, you'll see there CRV, okay, and that stands for chrome vanadium. It's a different alloy, not as strong as the chromoly. Now generally speaking, the impact sockets are sort of a black oxide finish, and normal sockets then have a shiny finish or some type of a more presentable finish. Don't accept this as guarantee though. Make sure that it's classed properly as an impact socket and not just painted black, okay? Now, just to add some confusion to the whole show, it is common to get adapters to allow an impact driver accept sockets, and vice versa with the impact wrench, where you can get an adapter to mount screwdriver bits in it. They're fairly straightforward to operate generally. They're like this. What they have is a hex drive on one end and then a square drive tooling on the other to accept sockets. So just for example's sake, we could mount that socket into our impact driver, and conversely we could do the same with our impact wrench. Now the one thing to remember here is that, number one, if you mount bigger equipment on your impact driver, you're looking at quite a small tool driving a big fastener, so you could overload this quite easily. And conversely with the impact wrench, you're operating a very big tool on very small fasteners then. So whilst crossover is possible, some common sense is needed that if you're going to do this, you know, you're not going to damage your tools, or, you know, damage your equipment or fasteners or whatever. Now what we're going to do next is we're going to head out to the shed. We're going to bring the impact driver with us, and we're going to compare its operation with that of a normal drill driver, which you get just a normal household one, and we'll see how we get on there. Now we're set up in the workshop, and what we're going to do here is just run a fairly simple timing test on a selection of different fasteners. These are a posi drive wood screw, which are about 125 mil long, which is just ever so slightly, sorry, they're 120 mil long, and they're just slightly under 5 inches. So what I'm going to do is first of all use the impact driver, and then I'm going to use just a normal small hammer drill with this hex driver head in it, and we'll just time it and see is there any inherent advantage in using impact drills, or is it easier on the system. And what we'll do is we'll time this as we're doing it. Okay, so we'll start off, timer, go, and we'll do this as quickly as we can. Right, we're at 26.15 seconds there. So what we're going to do now is do the same again, but this time we're going to use the normal small sized hammer drill, which is this fella with the bit driver mounted in the head, and we'll stick him to the higher speed on the gearbox and see how we get on. Right, set our clock, reset. Okay, ready, set, go. Right, and with our drill driver, we managed 22.65 seconds, so we're quicker with the drill driver. So we'll reset that. Now, where the advantage of impact tooling comes into play is in driving much heavier fasteners. And I'll just demonstrate that now. Now, we nicely demonstrated there that on a particular size of fastener that the impact driver doesn't have any advantage over a normal drill driver. So what we're going to do now is we're going to go to these 6-inch fasteners and we'll try them, and we're also going to try these lag bolts as well. Now what I'm going to do as well is do this one-handed so that it might demonstrate that the impact driver is easier to hold on to as opposed to the drill driver. So we'll give it a go anyway and just see what we're up to. Okay, we'll just start it first. Right, away we go. Now, as I was putting that in, there's significant reactive force on my wrist there. So that may be an advantage of the impact over the drill driver. And we'll just try the impact now. Same thing, one-handed, to see does this go in easier on the hand. We'll just start it again. Right, away we go. Okay, we've established there the drill driver does drive it in, no problem, but there's significant reactive force being exerted on my wrist, whereas the impact driver, you can just hold on to it lightly and it goes in. I'll just demonstrate that again now. Ooh, hot. Right, we'll start. Okay, and I'll just do this with one finger if I can at all. And we'll try the same now with the drill driver and see can we do it that way. Right, here we are, one-handed with the drill driver. We'll just start this off. Now, we'll try this. Yeah, there is significant reactive force there on the wrist. So that's one advantage of the impact driver over the drill driver, is that if you're doing a lot of fastening over the course of a day, the impact driver would be significantly easier on the wrists. So I'm just going to take these out now. We're going to try 2 lag bolts after that and see how we get on. Right, we'll change over now to what we have here is a hex drive to square tooling 1/2 inch. And we'll try this further down our piece of wood now. Okay, and away we go. Okay, we didn't get very far in there with the drill driver. We'll stick it down to the lower gearbox. Okay, touch of smoke out of something there. The back of the actual drill driver itself. And what we'll do now is we'll do the same with the impact driver. Okay, we can see the huge advantage there of the impact drivers, that they'll drive much bigger fasteners, no particular stress on the wrist, and it's not overloading the actual impact driver itself. Whereas we got a touch of smoke out of the motor of the drill driver over here. So I think that sort of establishes our case up to a particular size of fastener. the drill driver or the impact driver aren't going to have a huge advantage one over the other, except that the impact driver might be slightly easier to hold on to. But when it comes to much heavier duty fastenings, we're talking about a significant advantage with the extra power in the impact driver. Now we're back at the desk and we're going to talk about two things now before we head out to the workshop again and do a bit of testing. The first is the torque ratings on impact tools. There's no industry standards out there for manufacturers to conform to as regards what the torque capabilities of the tool are. Generally speaking, if you operate a percussive tool like that on a bolt, the longer hammers, the tighter it'll get. So there is limitations there as regards how long you can keep an impact tool on a bolt. Generally speaking, while it's not an industry standard, it is sort of recognised that working torque or normal working torque is classed at the operation of that impact tool for 5 seconds. Maximum working torque then is at 10 seconds, and then maximum torque is 15 seconds. So obviously if you need to spend 15 seconds tightening every fastener, this is a significant impact on time then, okay? So just keep that in mind. Now, one point to note is that if you are using impact tools and you put extensions on them, which is not uncommon by any means, this will decrease the torque capability because any play that you introduce in between the tool and the fastener by way of an extension introduces slop or play, and this will have an impact on the transmission of that impact capability. Now, on now to tightening and how to achieve a particular tightness on a bolt. When we use an impact tool, we apply torque to the head of the bolt, and torque is just a rotational force. That doesn't actually tell us how tight the bolt gets, and there are a number of factors then which impact upon that. For example, if we take a brand new M24, which is a 24mm nut and bolt, just under an inch, this is new, shiny and bright, and the nut is free running on it. If we take another M24 bolt, which is rusty, which is misshapen, and which has significant damage to the threads. I'm going to try and hold that up there so you can see that there's significant tearing of the threads there as we go up the bolt. If I apply the same torque to both of those bolts with a nut, the new shiny bright one will obviously end up much tighter than the dirty broken old one. So just the application of torque alone does not tell us how tight the bolt is. Now, 90%, as I said, of the torque that you apply to these bolts is lost through friction, both in the threads and the head of the bolt, acting against whatever material you're trying to clamp it to. Torque measurement or tightening bolts to a particular torque measurement from an engineering viewpoint, it's not a fantastic indicator. It's better than nothing, but not by much. There are other methodologies out there, such as turn of the nut method, which basically operates on you snug up the nut first, and then it tells you how many turns to tighten it after that to achieve a particular clamping force. There is also very specialized areas whereby you can actually measure the elongation of the bolt and how much it stretches by. And one of the reasons that there is torque ratings and clamping specifications is that to achieve a clamping force, a bolt will stretch, and that's normal to do so. But there's two different sections of that stretching. The first is called elastic, and when you release the tension on a bolt and there's elastic deformation, which is sort of stretching of the bolt, that will release and it will return back to its original form. If you over tighten the bolt, then what's called plastic distortion will occur, whereby the steel bolt or whatever material the bolt is made out of will actually distort beyond the point of recovery, and it will not return to its original shape or length. Okay, so that plastic distortion is what we're trying to avoid. Now, generally speaking, manufacturers of bolts, their torque or their tightness rating is generally to achieve about a 60% distortion of proof strength, and that proof strength is where you move from elastic distortion into plastic distortion. So on the right hand side of the screen there, I'm going to stick up 7 different size bolts, M6 through to M24. and I'm going to put in a manufacturer's torque recommendation to achieve the proper tightness on those bolts. Now, when it came to actually getting those torque specifications, there are an average of 6 different manufacturers. They range wildly depending on the material the bolts are made out of, and a host of other factors. Some manufacturers provide 4 different torque specifications for tightening a dry bolt, for tightening a lubricated bolt with possibly copper paste, molybdenum grease, machine oil, whatever. So it just, not to get too detailed into it, but it does demonstrate that there is other factors in play here other than just applying a particular force to the head of the bolt. Now we're going to head off to the workshop now, and what I'm going to do is put each of the bolts there that we put up on that particular chart or table into a piece of steel, and then we're going to tighten them using our impact tooling and seeing where they start to fail and how much pressure we can put on them. And one of the reasons, or probably the main reason I'm doing this, is to just demonstrate that using impact tooling, there's an inherent danger there that you can actually over tighten the fasteners that you're using and go into that plastic distortion section whereby the bolt is damaged and it's not going to provide the clamping force that you think it is. Okay, off we go. Now we're out in the workshop again, and what we've done is welded up our test jig. We've mounted our bolts with nuts on the rear. Some of them had to be built out because there's a non-threaded part on the bolt shank. And what I've done is I've arranged a number of spanners behind to counteract the force of the impact tooling. So we're going to start off with our M6, which is 6 millimeters, just under 1/4 of an inch. And we're using our impact driver, which is rated at 165 Newton meters. So we'll just see how this goes now in terms of how tight we put it and whether it starts to fail on us or not. Okay, that failed very, very quickly there, maybe 3 or 4 turns, and that was gone then. Okay, so that shows you that you have to be particularly careful with the very small fasteners. Right, onto the M8, and we'll try this again now with the impact driver before we move up to the bigger equipment. Okay, so off we go. So again, you see there the threads on the bolt failed. So we'll just give that one more spin now to see. Yeah, thread's gone. Okay, so that's M6 and M8 failed on the threads. They didn't shear the bolt or anything like that. So we're going to move on to the M10 now, and we're still going to use the 165 Newton meter impact driver. So the 10 millimeter is, you're getting into sort of a reasonably strong size bolt there. So we'll try that now. Okay, again, threads failed. So we'll just loosen that off now, get the spanner off it. Right, so M6, M8 and M10 all failed under full pressure of sustained torque from the small impact driver, and we're not talking about a particularly big tool here now. So we'll move on to the M12, see how we get on. Now, when we're looking at an M12, we're looking at nearly a 1/2 inch bolt there, so that's sort of a significant size. So we'll give that a go. Okay, we can see that the M12 now has held up fairly strong against this. I'd be surprised now if this had broken or stripped the threads out on the M12. Having said that now, I've no doubt that we've probably done some damage to this bolt. So what we're going to do now is swap over to the next wrench up, which is classed at 418 Newton meters. So let's stick that on there. And away we go. Okay, that had no huge problem in stripping that out. Now, and what we're at there, we're at an M12, again, half-inch bolt. So, right, move on to the next one. Right, we're on to the M16 now, and we'll just stick the spanner on that. And we're using the 418 Newton meter impact wrench. At an M16, which is 16 millimeter bolt, the 418 Newton meter impact wrench has not broken the threads on that. And just for information's sake, the M16 is classed as being a recommended torque of 205 Newton meters. So theoretically, we're doubling that force that we're applying to that, and it's still holding up. Okay, we move on to the big wrench now at this stage. And we'll see how we get on with the M20 and the M24. Now, I can't break the M16 because I don't have a socket suitable for that, for the big gun. But we'll move on to the M20 now, see how we get on. Just take this out of our way. Okay, that's snugged up. Now, what we're going to do here is, I don't know whether you can see inside in the handle there, but there's 4 different settings for power. So we'll start this off on the lowest one. And we're set to number 1 there. I don't know whether you can see that in there or not. Now we'll hold that there. Right, and we'll see how we get on. Now, the lowest power setting on this is 530 Newton meters. So, off we go. Okay, that held up to that. So, we'll move up the scale now. Right, onto power setting 2, which is 1,000 Newton meters. Okay, it's holding up to that. Next power setting is 1,800 Newton meters. Okay, it's holding up at the 1,800 Newton meters. Right, last power setting, which is 2,000 Newton meters. And we're certainly wearing the safety glasses here. we can see there that even at the highest power rating of that, which is somewhere around the 2000 Newton meter mark, our M20 bolt is not failing. I would say though that we've probably done damage to that bolt, even though it hasn't failed catastrophically. There's no point in going up to the M24 because we're not going to achieve any significant difference in bolt performance or whatever. But anyway, it just demonstrates how easy bolts fail under the pressure of impact tooling. Okay.